first, let's compute the asymptotics at x tending to plus infinity. In this case, the contour is simply the line from I to minus infinity. So here we put minus infinity. And let's compute the asymptotics. Well, we use standard technique, or the variant of Watson's lemma. Namely, we understand that due to the simplicity of our exponent function, the steepest, so the value of the integral is defined entirely by the vicinity of this initial point, which is t equals I. And we expand our exponent function in the vicinity of this point. Well, actually, we don't just expand, we decompose it into I plus rho times e to I pi. This is simply the parameterization of our variable, right? Pi means the direction, negative direction, and rho is the corresponding modulus of the complex number. The convergence regions for the integral is rho of the order of 1 over x, obviously, for larger x, so it's very small, and hence we drop here rho dependence in the denominator. Namely, we just change t plus I first to I plus I plus rho to e to I pi. And then we forget about rho terms altogether because it's the important rho are 1 over x. As a result, we get a simplified integral, which is just the first term in the general asymptotic series. So now rho changes from 0 to plus infinity. The exponential is turned into the product of xi, e to xi, and e to minus x rho. dt is turned into d rho with negative sign, and divided by 2I squared. So getting rid of additional 2 i's, we get the final answer, which is simply e to xi divided by 2I, and the elementary integration gives us 1 over x in the denominator, and if I didn't get anything wrong here, additional minus sign. And this is the correct answer. And next, what we in principle we should do, we should analyze the same asymptotics at x tending to minus infinity. However, you can check it yourself and prove that the asymptotics won't change its shape, so it will be again the same expression. So finally, we get the full answer for our problem. Keep in mind that indeed we recovered the bounded function for x tending to plus and minus infinity, and it's normalized by this normalization condition. So we actually extracted the most information about our solution which was possible at all to extract. So first, we got the exact form of our solution normalized by this condition, and the placement of the contour is defined entirely by their corresponding argument of x. And then we analyze the behavior, its asymptotic behavior at large positive and negative x. So, and here it goes. U of x at x tending to plus and minus infinity equals to, well, e to ix I divided by 2x. That's it for today. So I hope you enjoyed it, and let's switch to another discussions.